Here we have a graph of the function f of x equals x squared. F of 3 equals 3 squared, which is 9. The limit as x tends towards 3 of x squared equals 9 means that x squared approaches 9 as x approaches 3 from both sides. It's important to realize that when x approaches 3, x doesn't actually reach 3. Now there is a formal definition for the limit of a function which we won't cover in this course, but one way to interpret that formal definition is to say that the function x squared can be made as close as we like to 9 by making x sufficiently close to, but not equal to 3. So x approaches 3 from either the left or the right, but x never actually reaches 3. So I've circled out the point 3 here to indicate that what happens at 3 is not important. The value of the function at 3 is not actually important. Let's take this example. Let's suppose we want x squared to be within 0.000001 of 9. The idea is that we can always find two x values, both of which are not equal to 3, such that whenever x lies between those two values, f of x will lie between these two values. So I'm marking in the two x values corresponding to these two values of x squared. Neither of them is equal to 3. To get those x values, we just get the positive square root of these two values. To 8 decimal places, the square root of 9.000001 is 3.00000017. This number is very close to 3, but it's not equal to 3, and that's the key thing. The value of x corresponding to 8.999999 is 2.9999998. This value here is very close to, but not equal to 3. So, again, we can pick any two numbers as close to 9 as we like. I could make this closer to 9 just by adding in a few more zeros, and I could make this number closer to 9 by adding in a few more 9s. We will find two values of x corresponding to these two values, such that for all x in here between these two values, the y values or f of x values will lie between these two values. Let's look at a function for which the limit as x tends towards a certain value does not exist. In this case, the value is 2. Here the function is x squared for values of x less than or equal to 2. So that's the familiar parabola. And when x is equal to 2, f of x is 2 squared, which is 4. So this point is part of the graph. However, for values of x that are strictly greater than 2, the graph is a straight line. It's the straight line 2x plus 1. If we plug 2 in for x here, we get 2 2s are 4 plus 1 is 5. We get the point with coordinates 2, 5. That's this point here. And then the rest of the graph is a straight line. This is the equation of a straight line. We define functions to be single valued. So we cannot include the point with coordinates 2, 5, because f of 2 can only have one value. In this case, f of 2 is 4. It can't equal 4 and 5 at the same time. We define a function to be a graph for which a vertical line cuts it at just one point. So if we take the vertical line at x equals 2, it cuts the graph at this point. This point has been removed. So all the functions that we deal with are single valued. For each value of x, so x equals 2, there is a single value of the function, in this case 4. Now you can see that as x approaches 2 from the left, so x approaches 2 but never actually reaches 2, we could circle this point out, f of x approaches 4 from below. However, if x approaches 2 from the right, approach means never reaches 2, but we can get as close as we like to 2 without reaching 2, then if we go up to the graph for these values of x that are greater than 2, if we go up to the graph and get f of x, we get values of f of x that are greater than 5. So it appears that as x approaches 2 from the right, f of x approaches 5 from above. So we could say that the limit as x approaches 2 from the left, indicated by putting this minus sign, is 4. But the limit as x approaches 2 from the right, indicated by putting a plus sign, is 5. Since 4 is not equal to 5, that tells us that the limit as x tends towards 2 from either side does not exist. See, we want these numbers to be the same for the limit as x tends towards 2 of f of x to exist. Let's take a look at this function here. F of x equals x squared plus x minus 2 divided by x squared plus 2x minus 3. Now for this function, the domain cannot include the numbers 1 or 3. The reason is because if we try to get f of 1, well, the denominator gives us 1 squared plus 2 times 1 minus 3. That's 1 plus 2 minus 3. That's 0. As a matter of fact, the numerator gives us 1 plus 1 minus 2, which is also 0. 0 divided by 0 is said to be indeterminate. We cannot determine it. The reason why is because we could set this equal to any number we like. I could set this equal to 7. And you see that this makes sense, because if we cross multiply 7 multiplied by 0 will equal 0 multiplied by 1. Well, 0 multiplied by 1 is 0. You see, this is true. You get 0 equals 0. But of course I could have chosen any number here. I could have chosen 0.78 or 0.71 or anything at all, and this would also be true. I could set 0 over 0 to be minus 9.81 and it will still work out. So we cannot have x equal to 1 because the value that we get is indeterminate. What happens if we try to get the value of the function at 3? Well, plugging 3 in here we get 9 plus 3 is 12 minus 2 is 10. But in the denominator we get 9 plus 6. Actually this should be minus 3. If we get f of minus 3, we get plus 9 minus 3 is plus 6 minus 2 is 4. But in the denominator we get plus 9 minus 6 minus 3, that's 0. So we get 4 divided by 0 now. This thing does not exist. Let's suppose that it does exist. Well, let's suppose that 4 divided by 0 equals x, and we have to determine what x is. Well, if we cross multiply, we get x multiplied by 0 equals 4 times 1. You can think of this as x over 1. Well, 4 times 1 is 4. So we've ended up showing that 0 equals 4, which is nonsense. So f of minus 3 does not exist. Now let's suppose we want to get the limit as x tends towards 1 of f of x. We simply cannot plug 1 in for x in this case, because we get 0 divided by 0, which is indeterminate. Let's look at a number that's close to 1. Let's take 0.999. If you work this out to 5 decimal places, you will get 0.74994. Notice that to 2 decimal places, this is approximately 0.75. Here I have a value of x that's even closer to 1. Remember, we can take x to be close to 1 but not equal to 1. As close as we like to 1 but not equal to 1. So for f of 0.99999 we get this number here. This number is given to 6 decimal places, and you can see that this is even closer to 0.75. As a matter of fact, as x approaches 1 from the left or from below, f of x is approaching 0.75. When we say the limit as x tends towards 1 of f of x equals some value, we mean that x approaches 1 from either side. So now I'm picking a value that's greater than 1, but as you can see it's very close to 1, but of course not equal to 1. It's very important. If we work out the value of the function at 1.00001, we get a number that, as you can see, is very close to 0.75. And you know, the closer I make x to 1, I could have worked out f of 1.000000001. I will get a number that's even closer to 0.75 than this number here is. So the limit as x tends towards or approaches 1 from either side is 0.75. Here is a part of the graph of the function. At x equals 1, the function is indeterminate. We get 0 divided by 0. So I've circled out that point on the curve. So the function has no value at x equals 1. So 1 is not part of the domain. So we just have to circle out a point that's on the graph at x equals 1. As a matter of fact, the coordinates of this point are 1, 0.75. So as x approaches 1 from the left, f of x approaches 0.75 from below. And as f of x approaches 1 from the right, f of x approaches 0.75 from above. We can make f of x as close as we like to 0.75 by making x as close as we like but not equal to 1. Well, I should say we can make x as close as we like to 0.75 by making x sufficiently close to 1 but not equal to 1. So we could circle this point out to show that what happens at x equals 1 is not important. Now we can rewrite our function by factorizing the quadratic expressions. They both have factors, and actually they have a factor in common. That factor is x minus 1. And that makes sense because if we plug 1 in for x, this will be 0, and of course this will be 0 as we've seen before. So we'll end up with 0 divided by 0. 0 times x plus 2 is 0. 0 times x plus 3 is 0. We'll end up with 0 over 0 when x is equal to 1. But 1 is not part of the domain of this function. So x is never actually equal to 1 for this particular function. So x minus 1 is never 0. So, we don't have to worry about 0 over 0. And we can divide above and below by x minus 1. It's not like we're cancelling the two zeros. We don't have anything indeterminate like that. We have two numbers that are not 0 and are equal to each other, so we can cancel them out. And we can write our function as x plus 2 divided by x plus 3. So our function can be written like this. This is identical to what we had, as long as we clearly state that x cannot equal 1. So the graph of this will look exactly the same. We just need to circle out the point on the graph where x equals 1. So we just have to circle out this point. So the situation is the same as before. But now if we take the limit as x tends towards 1, we can actually get the correct answer by just plugging 1 in for x. So again, the idea is that we can make this thing here as close as we like to 0.75 by making x sufficiently close to but not equal to 1. And x can approach 1 from both sides, either the left or the right. Let's look at this new function g of x. Well, as you can see, this expression has the same form, but the difference here is that 1 is part of the domain. Notice now that the only value that's not allowed to be part of the domain is minus 3. Before, for the function f of x, 1 was not allowed to be part of the domain. So we say that this is a different function, even though this thing has the same form. It's just that the domain is different. Notice, however, that the limit as x tends towards 1 of g of x is also 0.75. No change there. Let's look at the graph. Here's the graph of g of x. This time the point with coordinates 1, 0.75 is included. Finally, let's take a look at yet another function. This function is called h of x. This part of it has the same form as the previous functions. But now, when x is not equal to 1, we work with this here. But when x is equal to 1, h of x is 3. So in this case, h of 1 is equal to 3. Let's see the graph of this. Here it is. We have to circle out this point because functions have only one value for each value of x. If we draw a vertical line through x equals 1, it's got to cut the graph at just one value, and it cuts it at this point here whose value is 3. So h of 1 is equal to 3. So we can't have that vertical line cutting this point. Our function has a single value for each value of x. Now as you can see, as x approaches 1 from either the left or the right, the function is actually approaching 0.75. It's not approaching 3. So this limit here is 0.75. Notice that this is not equal to the value of h at 1. So it's incorrect to plug 1 in for x here. We can't do that. So we can make h of x as close as we like to 0.75 by taking x sufficiently close to but not equal to 1. And x can approach 1 from both sides. We cannot make h of x as close as we like to 3 by taking x sufficiently close to 1.